All right, hello everyone. Welcome back to Physical Geology 1403. Today is lecture 12, the first lecture of module 3. Okay. Hopefully you will have taken exam 2 by now. If not, please take it ASAP so we can get that done. Module 3 is underway as of now. This is how the rest of the term is going to go. Today you are getting lecture 12 and lab 5. And the lab exam is opening. That sounds like a lot, but lab 5 isn't actually on the lab exam, so you can take the lab exam before even attempting lab 5 if you would like. Okay. For lab 5, we're going to do it a little bit of an interesting way today. I pre-recorded yesterday all the instructions for how to do lab 5 for my other class. So instead of taking the time to give you guys those instructions on how to do it live, I'm going to save us some time, post that recording for my in-person class and my online class, and then we'll have the rest of our in-class time to work on the lab exam or to catch up on labs 1 through 4, which you must complete before taking the lab exam. Okay? So yeah, that's how it'll go. Next week, our first lecture, or our first meeting of the week, is going to be lecture 13 and then final exam review. Because next week's the last week, guys. Man, how time flies when we have fun. Yeah.
I never said I was.
I can read it in your death stare.
I'm going to need you to go to UTPB so I can have a cool professor.
Aww. They did actually try to snag me a few years back.
Did you ever watch Boy Meets World? I need you to be my Mr. Beanie.
I never watched. What was it called?
Boy Meets World?
Boy Meets World?
Yeah.
No, I never watched that. I told you a little bit of my childhood. We moved around a lot. Like, we had a TV most of the time, but we never had cable. So if it was like on a show like the Disney Channel or something, and Disney Plus didn't exist back then, okay, guys, it was all cable. I never had cable, so we never really watched it or anything. Hey, what? Back in the day. In my day, we had to all get out and push the plane to get this started. All right. And then, yeah, so the first time we meet next week for your class, it'll be Tuesday for my online class. You know, it's just whenever I post the recordings, right? It's going to be lecture 13 and final exam review. That day, the final exam will open. You will have approximately 3 days, actually. You'll have 3 days to take the final exam before the end of the term. The term closes Thursday night at midnight. Friday is the day that I work on getting all of the grades turned in. So all assignments must be turned in by 1 week from today at midnight. All right, that's the cutoff. I come in Friday morning and I close everything and I grade whatever is turned in, and whatever wasn't turned in is tough luck. Okay. Let's see. So our second meeting next week for my in-person class, naturally my online students, you won't be required to be here. But on Thursday next week, we are having our class movie day. Okay, and that will be an opportunity for you to get a little extra credit. The movie is going to be 2012. That's officially won the vote. For my online students, if you would like to participate in this extra credit opportunity, you can watch 2012 on your own and complete the extra credit assignment that I will upload that will answer questions about the science in this movie. Okay, because the whole point is we watch a movie that has terrible science in it and we pick it apart and make fun of it. All right. For those of you that will be here in person, you can bring snacks, you can bring drinks, college-appropriate drinks. Okay. Boo. Yeah, we'll just have a fun, good time with it. Any questions about the rest of the course and how it's going to play out? No? One of my frogs is climbing on the glass. Let's see. I think that's all I've got to talk about. Any interesting, fun stories that you want to talk about? This is something that Chloe asked me about yesterday, and I told her, and apparently it blew her mind a little bit. The Arctic has polar bears, but no penguins, and the Antarctic has penguins, but no polar bears. And an easy way to tell, like to remember this, is Arctic. The word Arctic literally means bear. Okay? So when we give something, when we name something, we give it a genus and a species. We'll talk more about this concept in 1404, next term. But a genus and a species, bears are in the genus Arcturus. Okay? That's literally what it means in Latin is bear. So Arctic, bears, Antarctic, ant, the Latin prefix ant means no, nothing, no bears.
Your frogs had something to say about that.
Yes, they did. They're from Australia. They don't get a vote. Cool. Thank you for that little tidbit there.
I feel like a lot of people need to know that.
Don't know that?
Need to know.
Oh, neither know that? Yes. One of them is our president. He literally posted on Twitter last week about the polar bears in Greenland. Or the penguins in Greenland. He said the penguins in Greenland.
He couldn't even pronounce the name of the country of the, like, was it the president or whatever that he, like, kidnapped?
Oh, Maduro.
Venezuela's?
Yes, Venezuela's.
Oh, I do have a question though.
Yeah.
So, your good buddy Jonathan over in the music department,
Jonathan.
Ortiz.
Oh, Ortiz, yes.
Yeah. So I emailed him about my homework. He said I had until the 6th to get it all turned in. Is that
Until March 6th. That's his call.
okay?
What he's probably going to do is put off turning in final grades until literally the last second.
Okay.
I try and get things turned in. I'm the sort of person that hates procrastination in myself, and I tolerate it in others to an extent. But in myself, I can't stand it. So Friday is the first day we can get final grades turned in. Monday the 6th is literally, like, they will call you. If the people submitting final grades to the register, to the
Wait, that Monday.
records department, the 6th is Monday.
No.
What day is the 6th?
8th?
The 6th is the 8th? What day is the 6th?
Oh no, the 6th is on a Friday. Oh, it's next Friday.
Right. That's what I'm saying. All of them need to be turned in by. Bless you.
Thank you.
I just said that all of them have to be turned in by that day because that's the day that we can turn them in. On Monday morning, people in the records department will go in to submit grades for transcripts. If grades are not turned in by then, we get phone calls and people get mad at us. So I get all my grades turned in on Friday
Okay.
because I'm not working on the weekend if I don't have to. And I'm sure you guys understand.
No, you said Monday the 6th, and I'm like, that's not the 6th because that's the first day I have off to move.
Right. Yep. Okay. We were talking about
Polar bears are not.
Oh, yeah. We were talking about Trump saying Venezuela's. Did anyone watch the State of the Union? The longest State of the Union in history. It didn't need to be.
Adriel wants to know if it's final review day.
Final review day? No, tell him that's next week, but he should still be here because we're still having content he needs to hear. Unless he has extraneous circumstances, in which case he should have emailed me about it. Yeah. Talk about a speech that could have been an email. I mean, there were some important things in there. I don't want to downplay that. There have been some good things. There were plenty of other things that did not make it in the speech, though. He had the crew of the Artemis II rocket there were in that crowd, I believe, and completely neglected to mention the Artemis II mission. It was even a thing.
You're gonna be on a watch list.
Probably.
Adriel said it'll be on.
But here's the thing. I'm not the guy that will suck up to other people to get ahead.
They're not gonna put the Easter Bunny on the watch list.
Oh, I'm sure the Easter Bunny is already tucked away somewhere in Area 51.
Oh no, I think Santa Claus is on the watch list.
Santa Claus is on a watch list. He continuously breaks no-fly zone laws.
He's a stalker.
He's a stalker.
If you'd seen South Park, you would understand like the whole Disney being on the list already. Like apparently, what's his name? Pooh Bear.
Winnie the Pooh, yeah.
He's locked up in China.
Is locked up in China. That's funny. I have no doubt I'm already on watch lists.
He's got a whole record of public indecency.
So actually, my dad used to work at the Pentagon. And while he was there, so standard policy for ranking officers at the Pentagon is there's actually an analyst and their entire job is to sit in a basement and monitor the digital activities of at least several officers. So there was an analyst who monitored my family and I's entire digital activity for the whole time that my dad was working at the Pentagon. So if the government wants to monitor me, they know where to find me. I don't exactly hide myself. And I say things like this in front of camera all the time. If I disagree with someone or something, I'm going to do it. My whole goal in my future career is I want to make a difference from the way that things are happening right now. And things can't change if people don't point out the flaws. So, oh, she gave me the little finger clap. That's what I'm going to call it now. It's a finger clap now.
Clock it. Yeah.
It's called what?
Clock it.
Clock it?
Yes.
Clock it, please.
What does this have to do with clocking?
It's just a thing, okay, Josh?
It's recognizing somebody's correct,
No,
correct,
correct statements. Yeah. I get the meaning behind it. I just don't understand the name behind it.
Correct sassiness.
Correct sassiness. Okay. All right.
I guess it'd be like if you said like something controversial.
Like when
bad.
she
Got
told
it.
what's his face, girl, you do that. Correct sassiness.
Right. All right, let's get back to the subject here. What was hold on. What was that thing that happened the other week where we just kept coming back to it?
Of course, now I can't remember.
Yeah, you remember?
Elon Musk?
So that's the story of Elon Musk. There we go. Nice memory. All right.
No.
Let's talk about earthquakes. This is going to be Emma's favorite lecture because part of earthquakes is tsunamis. Yes.
When you get to the tsunamis part,
That's when she'll pay attention. First time in 7 weeks.
Until then, I didn't do my math, so it's okay.
All right. Earthquakes. Who can tell me what an earthquake is?
The shifting of tectonic plates that we can feel.
Whoa. I didn't ask what makes an earthquake. I asked what an earthquake is.
That.
My mom. I didn't ask what makes an earthquake. I asked what an earthquake is. Oh, self-burn.
Oh,
The earth shakes, exactly. It's not that complicated, right? Now, what causes them? Earth shaking is the expression of a release of energy. Where does that energy come from? Energy doesn't just manifest. It's not just there, right? It has to come from a source. And the source here is, you are right, the buildup of stress at boundaries. Now, there are two types of boundaries we've learned about in class. We talked about one pretty extensively already. Plate boundaries. Remember plate boundaries? There are the three. What do we call the one where the plates pull apart from each other? Divergent. What about the one where they crash into each other? Convergent. And the one where they scrape past each other?
friction?
I mean, yeah, it's making friction, but what do we call that boundary?
Tectonic plate. The fault line. Your mama, I don't know. Fault line.
You're allowed 4 of those jokes. You have already used 2.
I don't know. I'm just throwing things out.
Transform.
Yeah.
Yeah, it's a transform plate boundary where they slide past each other horizontally, like so, okay? So, transformer, right, sure, if that's how it helps. Now, there are also 3 types of faults, at least 3 that you're going to learn about today, okay? The first type of fault is called a normal fault. Now, let me tell you a little bit about, not NL, normal fault, okay? Faults are cracks in the earth, okay? They are cracks that are caused by the buildup of that stress, this tectonic stress, which eventually, once that stress builds enough, makes a crack in the ground. It breaks, and now there's a crack in the ground. Now here's the thing, just because it's broken does not mean that the source of that stress is gone. That stress is going to build up again. Except this time, when the stress is released, the crack is already there, and so the crack is just going to shift a little bit, releasing that energy, okay? My favorite example of this is asking everyone to put your hands together like so. Hands together. Hands together. Hands together. Okay. Put your hands together and push them at each other as hard as possible. And then try and move your right hand out in front of you. It takes a second, but then finally, it slips. That's exactly what's happening on these fault planes. Okay? The energy builds, it builds, it builds, it builds until the energy overcomes the friction holding the two sides together, and that release of energy makes an earthquake. So here we have our fault plane right there at a certain angle. The side of my fault below the angle of the fault. When I say angle, look at that angle that it's at right there. Yeah, here, let me do it this way. I'm standing in front of most of you. Okay? That angle right there is the angle. The side beneath the angle is called the footwall. The side above the angle, so on the obtuse side, we call that the hanging wall. In a normal fault, the hanging wall is moving down relative to the footwall. That's the motion along the fault plane. Whenever this slips a little bit and makes an earthquake, the direction of motion is hanging wall moving down. Then we have a reverse fault. In a reverse fault, here's the angle. Man, my black pen is dying. We've got our footwall, our hanging wall. Those don't change, right? Those are based upon the angle of the fault, not the direction of movement. Except in a reverse fault, the hanging wall is moving up relative to the footwall. So every time there's an earthquake, it's because there is a slip upward. Then we have strike-slip faults. So here's the angle of our fault underground, but it expresses on the surface as just a crack in the ground, like that. No one side moving relative to the other above or below. Whenever there is motion along a strike-slip, it is horizontally like that. Do these three faults look familiar? Do they remind you of anything? The plate what? The plate boundaries, just so. Okay, so we have our hanging wall here, where one side is moving down relative to the other. What kind of force is causing that? They are pushing opposite directions. Whatever tectonic force caused this normal fault is causing these two halves to move apart from each other. One side is slipping down on top of the other. What about this one, where one is shoving up on top of the other? Yeah, that's the equivalent of a convergent boundary. There is some force pushing these two halves together. And what about a strike-slip fault?
Transformer.
Exactly, where they are moving in opposite directions horizontally. The same forces are happening here. For a plate boundary, they happen, you guessed it, at plate boundaries. On the edges, faults occur on the inside of plates, where the same forces are being applied, but there is no nearby boundary for them to express. Okay? And so the ground cracks and shifts according to those same forces. Okay? So these are the different situations where we can get those earthquakes, faults and plate boundaries. Now, what is an earthquake? When we get some slippage along a fault plane, and this is our fault plane in this case, okay? Yeah, it usually does have some sort of curvature to it like that. Whenever we get some slippage, the location where that slippage occurs, that's called a focus. Okay? So now it's moved over there, I guess. Hold on, let me go back here and I'll explain about it. Okay, so we have our focus. That is the location where the movement occurred. That means that any energy that is expressed because of that movement is going to radiate from that source. When I take a rock and I drop it in a pool, what happens? It sinks, but what happens to the water? It bloops.
It boots. And then there's a,
And we call those?
I don't know, waves.
No, little waves. Ripples, yeah, in water we would call those ripples, yeah? So what's happening here is my movement is occurring, energy is released, and when energy is released from a single point, it radiates outward in a three-dimensional direction, okay? All directions, 3 dimensions. You ever seen anything like a video of an explosion in slow motion? You see that shock wave go out in every direction? Think of that. This energy from this earthquake is released as an expanding sphere radiating outward from the location of movement. Now it's going to stay a sphere of energy as it moves through the ground until it reaches something. It's going to reach the surface. Okay? When it reaches the surface, here's our focus, okay? Here's our waves of energy radiating outward. What do we call a sphere on a two-dimensional plane?
Circle.
A circle. So when that sphere reaches the two-dimensional surface of our planet, it's going to look like there's a central point and everything is radiating out from that central point on the surface. We call that central point on the surface the epicenter. You've probably heard that term. Epicenters are on the surface directly above the focus. So if the focus is 15 kilometers underground, energy radiates from there. When it reaches the surface, it looks like an expanding bullseye of energy moving across or rippling across the surface of our planet, just like what happens in water when you drop a rock into it. Okay, so there's your epicenter. Now, the waves that manifest on the surface are what cause all of the damage from an earthquake. Okay, the intensity of your earthquake determines how large your waves are going to be and therefore how big the damage will be. Okay, we'll talk more about that, how we measure that and everything in just a few minutes here. So we have a plane, be that a fault boundary or a fault surface, okay, a fault plane, along which energy is building. That energy builds and builds and builds and builds until this energy, which we call elastic energy, by the way, overcomes the friction of the fault surface. You're already familiar with this concept. You pull on a rubber band, you're going to pull on it, adding elastic energy until one of two things happens. Your material breaks, or the energy in that rubber band overcomes the friction of your fingers holding it. And it slips out of your hand and snaps your other finger. And you go, ow, right? Either one of those two results, the breaking of the material holding the energy, or the snapping back effect of the material that held the energy, will result in an earthquake in nature. Okay? This is the physics behind what makes those earthquakes. Elastic energy overcomes friction. So when we are measuring earthquakes, we will use devices called seismometers. I'll show you some of those in a minute. But those seismometers, they pump out seismographs that look like this. When we are studying earthquakes, we will often see, prior to the earthquake, tiny little ground movements. We call those foreshocks. Anything like that, tiny little ground movements that happen after the earthquake, because the earthquake sets off a lot of the time a chain of events, we call those aftershocks. Okay, so we have foreshocks, the main event, and then aftershocks. All right. So you can see on the seismograph, we're reading, there's a bunch of little foreshocks happening, and then not a whole lot going on, and another foreshock, and then big earthquake right there. Yes, so where this is right here, this is where the reading is newest, okay?
What? Person came up with this was not from America, where should we read left to right?
It's drawing left to right. The needle to draw this is over here on the left side. Maybe it'll make more sense when I show you the device that actually makes this. Okay? So here we have another overview of those faults I was just talking about. The largest fault along which earthquakes are common is the San Andreas Fault. You probably have heard of this fault. Okay? This is the San Andreas Fault. It goes all the way from Northern California all the way down here. Okay? And it's very dangerous because every 100, 150 years or so, it'll pop off with another big earthquake. The last one was in the early 1900s. Is it 1919 or 1929? I want to say 1929. 7.9 earthquake. It was a 7-point-something earthquake, I believe. But pretty much leveled San Francisco. Okay. If you've seen the San Andreas movie, which Emma clearly has.
Jillian had.
What was that look?
That's the one I wanted to watch.
I know that's the one you wanted to watch. But the people have spoken.
Wait, which one are we watching?
No, there was one back in the 20s. Huh?
Which one are we watching?
2012.
Okay, well, it has a tsunami in it, so I'll let it
It
slide.
does. It does. What was I saying? Oh yeah. So if you've ever watched the San Andreas movie, there's a part where they're in their truck, a truck that they stole, I think technically, right? And they're having some sort of soulful moment. They're revisiting some backstory about their daughter. They're having some sort of conversation, and they come to a screeching halt because the road has been broken. And they get out of the car and they look down, and where the road that they're standing on, the other half of the road is across like a 60-foot chasm and like 40 feet further down. It's offset like this. And then The Rock does that thing where he kind of looks off in the distance and he does that smolder and he's like, it's the San Andreas fault. Right? Yeah, I did pretty good with that, right? Yeah, that was, hey, she clocked that one. I did good. I sounded like The Rock. All right, great. So, there's a huge problem with that. What they are showing is vertical offset. Okay? Which one of these two things were they looking at? So if they're on a road, right? And they're looking at across a chasm and the road continues on the other side of that chasm with vertical offset, they were looking at a normal fault. Here's the problem with that. Even the San Andreas fault isn't a normal fault, it's a strike slip fault. There would be no vertical offset. There would be no, the road is up here and down here. If the San Andreas fault shifted, the road would be here and right there. Also, there wouldn't be a chasm. They were looking down, there was like a hundreds of foot deep chasm between them and the other side. There would be no chasm on any kind of fault because the whole point is that the two sides are pressed up against each other so hard that they have an earthquake when they slip. If at any point they separated from each other, we would no longer have a fault, we'd have a canyon. There would be no pressure to release. So for a couple of reasons, that doesn't make sense geologically, but it looked really impressive on the screen, which is why they did it.
Okay, but it's no fun doing it the correct way, okay?
Well, that depends on whether or not you appreciate
I mean,
correctness.
talk to the old couple who just so happen to own a plane and get on the plane and fly over, okay?
Right, exactly. That sort of plot convenience I can overlook if the fault looks correct.
Whatever.
So it says that regular significant ruptures were in 66, 34, 22, 01, and 1881, but there was the Great Francisco earthquake in 1906.
06, that's what I'm thinking about then. 06, thank you. I knew it was sometime in the early 1900s.
Yeah, it says it has the regular significant ruptures about every 22 years.
Yes. Yeah, they'll get those, but
Are those just their like normal bad earthquakes?
normal bad earthquakes, sure. The really, really bad ones, like the one in 06, those are absolutely devastating. Yeah.
Like leveling?
Yeah, like level the city. We'll get to that later on. All right. So this is a seismometer right here, a classic seismometer, I will say. So I actually have a demonstration model that I built right here.
That is so nerdy.
It's so nerdy. I don't have a problem with that. All right. So how does the seismometer work? Let me tilt it a little bit this way so you guys can all see. Here we have a device that is attached to the ground. This plate is attached to the ground. This pivot arm is attached right here at a near frictionless surface. On this end, there is a pen which is just barely touching a roll of paper wrapped around a drum. This drum is constantly rotating, like so. I actually built it so that I could attach a drill. I have a drill I can attach to this, and I have the drill's button taped down just right, so when I plug it in, it goes at the right RPMs to make this work. But it's a lot of work to set up, and sometimes it works and sometimes it doesn't. Huh? Great. Okay. So I just didn't do that this term, though. Okay, so what happens is during an earthquake, the ground is shaking, moving back and forth. As this plate, which is attached to the ground, moves back and forth, this arm remains in place and wobbles back and forth across this paper as this rotating drum is moving. And it draws waveforms. The amplitude, this is the cool part, the amplitude of the waves on this paper is exactly equivalent to the amplitude of the earthquake waves in the ground. So, why is that important? Why is that impressive? Well, that gives us a frame of reference. It lets us know actual data about the earthquake that is measurable and comparative. We can compare the amplitude of many earthquakes and make calculations based upon that data. This is called the science of seismology. So, seismology uses seismometers to make seismographs and understand earthquakes. You hear seismo, think earthquake. Okay?
Seahawks fans set off the seismometer?
Okay, so back during, I forget what game it was, years ago, a couple years ago now.
Saints fan.
You're a Saints fan.
Yeah.
Oh,
I think it was the 2014 wild card round.
yeah.
The Beastquake.
Uh-huh.
That was like their news jersey this year too.
Oh, really? Was it?
Yeah, the one that they played against the second game against them.
Yeah.
I'm pretty sure that was the jersey they wore. My husband was very excited.
Yeah, the noise and stomping and everything from the crowd was so powerful that it did register on earthquake measurement devices. These days, we don't have too many seismometers that look like that. They are more compact. They're more digital. I actually have 2 small seismometers sitting in my office that are going to be installed here at OC in the next couple of weeks, fingers crossed. Okay, so we can measure the earthquakes around here for ourselves instead of relying on other people's data. So essentially what it is a little microcomputer about this big with a little spring, a very, very carefully calibrated spring with sensors on it. And when the ground moves and the spring wiggles back and forth in its little housing, the amplitude of that movement is registered as the amplitude of the earthquake. So no longer is there a little pen on an arm that does that. There's a little tiny, very carefully balanced spring that'll wiggle back and forth. And we read that digitally, and then it's transferred to a computer. But the concept is the same, seismometers measuring the amplitude of the earthquakes. This is an old device that was built in China in about 3,000 years ago, which had a very carefully balanced weight in the middle of this big egg structure. And whenever an earthquake encountered the structure, the weight would remain in place while the egg container moved and would push this arm out, causing a ball to drop out of this dragon's mouth and into a bowl at the bottom. And then whoever's in charge of watching this thing go clonk, they hear a clonk, they're like, oh, we just felt an earthquake. It came from that direction. How do they know what direction it came from? Because the direction that the egg moved caused the arm to push the ball out on the opposite side. So the Chinese have been studying this sort of thing for a long time, right? Pretty cool. All right, now let's learn a little bit about the waves that come from earthquakes, okay? So there are 2 types of waves. Surface waves, which are the ones that occur on, you guessed it, the surface. Okay, those are the ones that cause all the damage. We don't live underground, so underground waves are irrelevant to damage. The ones on the surface are the ones that cause all the damage. Then we have body waves. To demonstrate body waves, I have another model. I like hands-on learning and teaching. Okay. There are 2 types of body waves, primary waves and secondary waves. Primary waves are, there we go. Primary waves are push-pull, compression of mass. Let me turn this a little bit so you guys can see that easier. Okay. It's compression of material in response to the energy of the earthquake. What do I mean by that? Well, watch what happens when I give this spring. Do you guys know what this is called, by the way? It's a slinky, yeah. These used to be really fun toys back in the day.
Oh, slinky.
Yeah, it's a slinky. Watch what happens when I give this slinky a little bit of energy in this direction. Am I pushing it all the way to the back? Am I doing this? No. But what's happening here? I'm giving it a little energy, and what's the slinky doing?
Vibrating.
No. Here.
Domino effect.
Turn it so you can see that easier.
I don't know what to describe that, Josh.
The best way I can think to describe it is domino effect.
Shoot. Tell me what. Explain.
Like a domino, you line them up, push it over, and then the rest fall. So it's kind of just following the movement that you first created.
It makes me think of
I see what you're saying.
ripples in water.
I see that. Okay, so I am giving it a little bit of energy, but what's it doing with that energy? That energy is transferring through this object in the form of a compression wave. Watch. The energy is causing the slinky to compress. No part of the slinky is actually traveling from point A to point B. All of its mass is staying in the same place. What is transferring? The energy through compression of the different parts of the slinky all the way down. This is a primary wave. Compression of rock instead of compression of slinky. Yes, rock can compress. So a compression wave, this primary wave, is compressing rock on its way through it. Okay? Then we have secondary waves. Secondary waves move at right angles to the direction of energy given. So watch what happens when I give this object energy in this direction. Notice what direction the mass moves in. What direction is it moving in? I don't want this to fall off, so let me do it again.
I think that's not the most stable thing.
No, it's not, but I can't build anything more stable without attaching it to the surface of my desk. What direction is my rope moving in?
Down and up.
Down and up. I'm giving it energy that direction, and in at what angle is it moving?
9.
Yeah, at right angles to the energy I am giving it. That's what secondary waves do. So we have compression waves, and we have...
He refuses to
Tell him he can sit in my lecture whenever he wants.
You can sit in the lecture whenever you want. Go check on the
So, these are the two types of body waves, and they actually have practical uses as well. For example, primary waves, compression, will travel through all different mediums, solids, liquids, and gases, because all three of those are compressible. However, secondary waves will only transfer through solids. You cannot force a fluid, like gas or liquid, to a right angle of energy that you are delivering to it. Okay? So, that being the case, if I were to send primary and secondary waves underground and know that primary waves will pass through all different states of matter, but secondary waves will bounce off of fluids, can you think of a situation where that would be useful as a tool? Is there an industry maybe that might like that? Are there any industries that make all their money off of fluids that are underground? The oil and gas industry. And water as well, by the way. I know.
I'm not talking about that, Justin.
The secondary waves, I'm going to treat it like you just had a revelation about something I said, though.
He's waiting for this tsunami.
No, we'll get there. We will get there.
No, I'm crashing out over my internet right now, but
OC internet sucks all the time. Yeah, if you see primary waves pass through layers of rock, but secondary waves bounce off of them, pretty good indicator you're looking at layers of rock that have some kind of fluid in it. Now, is it oil or is it water? You have to do other tests to figure that out. But this is a first step. Okay? So now that we understand more about earthquake waves, how do we locate earthquakes? How can I confidently say there was an earthquake last week off the Kamchatka Peninsula in Russia, about 67 kilometers off the coast, 10 kilometers underground?
Based off the strength of the waves we receive,
Receive with what?
our seismometers.
Based off the strength that we receive from our seismometers. Here we go. Here I have 3 seismograph readings. One from India, one from Australia, one from France. It was in India? Well, let's see. Okay, so a seismograph is going to give you a couple of pieces of information. As earthquake waves pass further and further through the ground, their amplitude gets weaker and weaker. Okay? The energy is getting diffused, basically. P waves are found first, are intercepted first. S waves intercepted next. Okay? So what that means is that I can look at the distance between a P wave and an S wave, and that also gives me a clue as to how far away my earthquake was. Notice the distance between the P and S wave here and there, right? So how can we use these 3 readings to figure out where this earthquake happened? Let's use a practical demonstration. Here is Cole. Cole, you heard a noise. What noise did you hear? Huh?
The sound of like everything moving.
No, just pick a noise, any noise.
Oh, okay. It's like a scraping noise.
A scraping noise. A mysterious scraping noise has reached Cole's ears, and he wants to know what made it. He heard that noise coming from this direction. That's his only point of reference. It's not terribly useful, though, because to his perspective, that's half of his perceived world. Everything behind him couldn't have been that way. He heard it come from that way. So half of his perceived world could have been the cause of that noise. What do we need?
Is it a repetitive noise?
Irrelevant, whether it's repetitive or not. There is a noise.
I was like, if so, we follow it.
We need another data point. Jared heard that noise as well. Except for Jared, it came from that direction. Okay? So what has this done? It's narrowed the field. We've gone from half of Cole's perceived world to a quarter of their shared perceived world. We've reduced where it could be coming from. There's a pattern here I hope you're recognizing. Okay, what do we need to narrow this even more? More data points. So if we have a third one, Sergio heard that same noise. Okay? Except for him, it came from that direction. Okay. Now that we have at least 3 data points, I can say with certainty that the noise came from within this shape, this triangle. Do you know what we call this process?
Triangulation.
Triangulation, okay? So we have seismographs all that come from all over the place, okay? Seismometers set up all over the place, seismograph readings coming from all over the place. And because we know approximately how long the distance it is for when you start losing energy in an earthquake wave, we can do some calculations, okay? Triangulation. So how would I figure out where exactly that earthquake occurred? I have an equation. And I give you the equation here, and I don't make you calculate anything, okay? I'll just do it for you. S time minus P time multiplied by about 8 kilometers per second. 8 kilometers per second is a generalization, okay? Certain types of rock let waves pass through it faster, some slower, but 8 is a kind of an average. It's treated as more or less as an average here, okay? So when you clock all of this, when you add all of this in and you calculate it out, you get values in kilometers, because this is time in the numerator, this is distance in the numerator, and time in the denominator. So those seconds cancel each other out, leaving only a value in kilometers. So if we were to do that for this Nagpur, India reading, here's where the seismometer was that picked it up. The result of that equation would be 3,400 kilometers. What does that mean? That's a radius. That's the distance between the source of the earthquake and where it got picked up. But that means anywhere along that radius is where that earthquake could have occurred. What do we need? More data. This Darwin, Australia seismometer also picked it up. When you plug in that equation, it gives you, hard to read, but I think that's about 4,800 kilometers, okay? That gives you another radius and therefore another circle. Now, on their own, there's any number of places where this earthquake could have occurred, but together, we've narrowed it down to one of two places, where the circles overlap here, or where the circles overlap here. What do we need? One more data point at least. This Paris, France one picked it up and gives us this circle. And look at that, all three of them meet up right there. And that is how we know where earthquakes are. That's why on my phone, I get an alert about earthquakes only minutes after they happen. Because it takes that long for the waves to spread across the Earth, be intercepted by seismometers, and our collective database to spit out the calculations for where it happened.
Where is that?
That's in the Himalayas. That's actually, see, here's Tibet over here. This is actually southern China.
I thought it was in China.
Yeah, so here's Japan. Here's Korea. Yeah, so it's south central China. Bouts. Okay, any questions about that? No, pretty straightforward. All right, so now that we know where earthquakes occur, how do we measure these things? Why is measuring them important to begin with?
See how big the earthquake was? Like, moving-wise?
Right. So we can know historically how big they are. We know how big they are and what the results of the event was. Then maybe we can help forecast future events or prevent the same level of damage, right? So how do we describe how big they are? How do we record that? Well, this is called the Mercalli Intensity Scale. The Mercalli Intensity Scale goes 1 through 12 and is based entirely upon the damage caused by the earthquake. Mercalli 1, no damage, barely even felt at all. Mercalli 12, total and utter devastation, catastrophic. And then there are obviously intensities in between. This is very helpful for organizations like governments, the American Red Cross, and any other organizations who are built entirely on responding to these things in the wake of the damage caused. Why would this method of describing earthquakes be unhelpful for science? Unhelpful. It's obvious why it's helpful for governments and organizations that respond to natural disasters, but for me as a scientist interested in studying earthquakes, why would this be an unhelpful measurement?
Because it's built off damage.
It's built off of damage, and why would that be a problem? What do you think, boys?
I want to say maybe like the results can be inconsistent.
Inconsistent, because they're based on what?
Damage.
Which is based on, for something to be damaged, it has to be there to begin with.
Yeah, but they can also get more prepared, which means possible.
I'm not trying to say that this is not a useful measurement. It's just not useful for science. It's based on damage, which means that inherently there must things to be damageable there. So what if I have an earthquake in the middle of the Serengeti of Africa And the only thing that happens is a few villages have collapsed roofs and a fence falls down and the goats get out. That would be like a Mercalli 2, maybe, right? The giraffes got loose. I'm not sure they keep giraffes in pens, really, but maybe the giraffes got startled, right? But then you take that same earthquake and you drop it in the middle of New York City. And you have collapsing skyscrapers. Now we're talking about a whole different ballgame when it comes to Mercalli. So Mercalli is great for organizations that care about knowing about damage, but for science, it has no comparative value.
So it's only useful in densely populated areas.
No, it's not useful anywhere for science.
Well, not for science, but really that.
Right, like I said earlier, it's very useful for other organizations, but as far as scientific reference is concerned, the Mercalli scale is useless because it's based entirely upon whatever infrastructure was there to begin with. In science, we measure using the Richter scale. The Richter scale goes 1 through 10, and it is logarithmic. Do you know what that means? Increasing powers of 10. Right? Emma, you're working on math. You know what logarithms are, yeah?
Yeah, I took
She
that-
might, but she's not happy about
I
it.
took that last semester. Forgot about.
Don't even chastise me right now.
Oh, I'm not chastising. I'm talking about math.
Yeah, you're chastising me. How dare you bring up this subject?
Oh, that's not, yeah.
Evil subject.
Evil. So, the Richter scale is logarithmic. It has increasing powers of 10. That means that a Richter 1 is 10 times, or a Richter 2 is 10 times something than Richter 1. In the case of the Richter scale, it is amplitude. Increasing by powers of 10 in amplitude, which equates to about a 32% or a 32 times increase of energy, okay, every time. So a Richter 2 has 10 times the amplitude of a Richter 1. A Richter 3 has 10 times the amplitude of a Richter 2, but 100 times the amplitude of a Richter 1, and so on and so forth, with increasing amounts of energy every time as well, okay? So here is our Richter 1 through 10 with a few comparative energetic events that have occurred here. Okay, so the Hiroshima atomic bomb had the equivalent energy release of about a 6.2 earthquake. The Mount St. Helens eruption had the equivalent energy release of about a 7.8 earthquake. The largest nuclear weapon ever tested, the Tsar Bomba, had the energy release of about an 8.1. You remember I told you guys about this at the beginning of the course? The one they blew up in northern Russia, shattered windows all across Europe with the shockwave.
Sure.
You may not have been there.
I don't remember that many weeks ago.
Yes, it was not that many weeks ago. It was a month and a half. Come on. All right. The last time a supervolcano erupted, Krakatoa in the 1800s, had an 8.5 equivalent of energy. And the largest earthquake ever recorded was a 9.6 in Chile. Now, this is energy equivalent in kilograms of TNT high explosive. So when we're talking about a Richter 10, and when I say Richter 10, think just a little lower than that for the one in Chile, right? We're looking at, let's see, that's hundreds, it's thousands, millions, billions, trillion, 50 trillion kilograms of TNT high explosive energy equivalent, right? It's pretty intense. That is a lot of energy release. This all is independent of wherever the earthquake occurred. This is just data about the earthquake itself, okay? Measurable, comparative to other events. Most earthquakes occur in these mountain ranges, the Circum-Pacific Mountain Belt and the Alpine Himalayan Belt. Can you tell me why? Why would earthquakes occur in mountain belts? Because they are places where the plates are interacting violently. The fact that there are mountains there at all means that there is some pretty intense plate boundary action. Exactly. Now let's talk about the dangers associated with earthquakes. The first one being the obvious, seismic waves. Seismic waves cause the ground to shake. The stuff we build typically does not like being shook, right? We build with a lot of stone and steel and glass, and that stuff will break and shatter and bend, and buildings will collapse, okay? Interestingly enough, older wooden structures tend to survive earthquakes better because wood is flexible. It will flex to a certain extent before it breaks. Steel, not so much. Glass, shatters. Rock, not flexible at all, right? So seismic waves, big problem. You really don't want to build your structures on loose sediment in earthquake-prone zones. Why? Well, because if I have water, a water table that is close to the surface, as that earthquake shakes the sediment, it's going to bring the water from the water table, that groundwater, up to the surface, and it's going to turn your sediment into mud. This is called liquefaction. Liquefaction is very dangerous, as the owner of this vehicle found out when his street turned to mud. You can look up pictures online of entire apartment buildings where the bottom 2 floors have gotten sucked into the ground by liquefaction during an earthquake. Now, the moment that shaking stops, the water table stabilizes, your street turns solid again. You got to dig that car out, right? That is called liquefaction. Then we have ground failures. Okay, subsidence. Subsidence is when you have caverns or some other void underground, and the shaking action causes the ceiling to collapse. Well, the ceiling of that cave is the surface of the ground above it. So as the ceiling collapses, the ground collapses with it, and you get sinkholes and such. Big old pits in the ground. Okay, fire is another problem. Our cities are filled with gas lines and thousands and thousands of gallons of gasoline underneath of every gas station, right? We have power lines all over the place, water lines. When any of those things gets ruptured and interacts with each other, there are problems. Water mixes with oil, that oil gets transferred all over the place. It'll light up like this. You introduce an electric spark from a broken power line to that, and it lights the whole place up. You put an electric wire in a puddle of water and you step in it, you get electrocuted. All sorts of problems are associated with this because of the infrastructure we've built. San Francisco actually ended up burning down from that 1906 earthquake.
Oh, I have a book about that.
Yeah?
Yeah.
It's actually very rare to find a building in San Francisco now that's older than that earthquake because most of the city got burned to the ground.
Emma, is it an actual black book?
Let me see if I can find it.
Okay. And then finally, tsunamis. Tsunamis are the last big threat I want to talk about here. Because these videos weren't behaving when I lectured yesterday, I have to do a little finagling here. But I will get these videos for you guys. Okay. This is what causes an earthquake, okay? So we have 2 plates that are converging with each other. One is diving under the other. Subduction, right? Emma, I'm talking about tsunamis.
Come here. What is this one?
The San Francisco Calamity by Earthquake and Fire, told by eyewitnesses, including graphic and reliable accounts of all great earthquakes and their volcanic eruptions. Cool.
Yeah. It's
That-
really old.
That looks, you have that book?
Yes.
What? I want that book. All right, here we go. Tsunamis. So, tsunamis are caused by subduction of one plate under another, okay? Emma, you gotta pay attention to this part. Okay, so as one plate is diving under the other, it causes the overriding plate to kind of buckle a little bit. Eventually, that buckling effect is gonna pop back up. And as that crust pops back up, it pushes the water above it upward, and that's what makes a tsunami. So here, watch this video, and you'll see what I'm talking about. Here's Indonesia. Okay, Indonesia is right next to a convergence zone, subduction plate boundary. Underneath Indonesia, I know. Come on.
Yes, hit the board.
Hitting the board always works. Here we go. Okay. No, why did it skip? Here we go. Okay, so you can see the subducting plate pushing underneath causes the overriding plate to buckle down a little bit. And then eventually it releases, pops back upward, and when it does, pushes the water above it up.
Wait, you can like literally see the plates like subducting? Like,
When you look at them in cross section, yeah.
Oh my gosh, that's really so cool.
Yeah.
I'm gonna start digging on the seafloor.
Oh, you'd have to, what we just saw was several miles of cross section. Now, let me show you this one. On December 26th, 2004, there was an earthquake in Indonesia, and it made a tsunami 33 feet high. And this is video footage taken from that earthquake. These people are on the third story of their house or of their building. It's doing it again. It might. There we go.
really hard judge the quality of the video, but I remember because of the
Yeah, 2004. And it's Indonesia. They didn't have like the best cameras either. It is ripping apart houses. Like most of their community is gone. Most of it's underwater. It's terrifying. Let's think about how serious this was for a second. There are thousands of islands in Indonesia. How many of them do you think are more than 33 feet above sea level?
Probably not a lot.
Not many of them.
I feel like there's not a guy.
No, there are. What happens when your island, where the highest point is only 20 feet above sea level, gets hit by a wave that's 33 feet tall?
It probably just takes it back to the sea.
Your entire island is underwater. Hundreds of thousands of people that we know about died from this. But here's the thing. So I actually remember this day vividly, like it was yesterday. Thank you for that. I was 11. So it's December 26th. It's the day after Christmas. I was sitting on my living room floor playing with my toys that I got the day before. I was 11. I still got toys at 11. We still get toys when we're 11 years old. Come on. As one does. The year before you were born.
4 years before.
And we were watching the news. We saw this video and others like it getting shared around the world live. And it sent chills down my spine. It was terrifying. And my dad gets a phone call. He worked for the Navy as an industrial hygienist and toxicologist. He gets a phone call, goes in the other room, comes back with a bag and says, they're deploying me to Indonesia so I can help. And he walked out the door, and I didn't see him again for another 6 months. He was out there like that. Yes.
He said, Merry Christmas, love y'all.
Yeah.
See y'all later.
We didn't see him again until July the next year.
Oh.
Because most deployments, like, you have like at least a few days of repair, right?
Yeah, not for emergency deployments like this, though. So his job specifically was being sent to the islands that had been either partially or entirely submerged. Because what happens to your sources of fresh water, every stream, every lake, if a wave of the ocean washes into it? It's all salt water now. They had no fresh water, and they deployed him out there and other people like him ASAP so that they could start training the local populations how to purify their water again. So he came back with a lot of stories, though. He told me about islands that once had entire communities on them, but he landed his helicopter there, and there was no evidence that any humans had ever lived there to begin with.
Oh my gosh, that's crazy.
Not a single scrap of garbage, no foundations, everything washed completely clean. There were islands that had never seen white men before, because there are thousands of islands in Indonesia, and he landed on a helicopter. It was 2004, right? So he made quite an impression with that. There were islands where more people died than survived, and the survivors couldn't waste time burying their dead. They were focused on surviving. So they just piled them up, and there were piles of bodies stories tall. And all they could do was just let the animals eat them. It was pretty bad. So there are hundreds of thousands of deaths from this that we know of, but it's my opinion, based off the number of islands, that there weren't even records of how many people lived there. And people have lived in Indonesia for thousands of years, by the way. Every single island almost was inhabited. I think it would be closer to 500,000 dead from this event. I think, what was the last total? You want to look up what the most recent death toll from the 2004 earthquake was?
I love that you asked me. I Google everything.
I am all about fact checking. And the thing is, this number updates all the time because they're still finding evidence of people that once lived and no longer did after the fact. What's the current death toll?
230,000.
230,000 confirmed deaths from this, but I still believe it's probably closer to 500,000 when you take into account how many uncertain islands or how many uncertain populations there were.
Across 14 to 15 countries.
Right, Indonesia is very large. It hits Sri Lanka, Thailand. Right. I'm talking about total from this event because there's all those islands in between. Because it hit Southeast Asia, North Australia, it hit Sri Lanka off of Indonesia, or off of India, hit a lot of places. Okay. But yeah, this is an extremely visceral reason for why we need to pay attention to earthquakes, right? Tsunamis are a very common result of this. As a matter of fact, the earthquake, there was an 8.4, 8.5 earthquake in northern Russia, northeastern Russia last year that made a tsunami that traveled across the entirety of the Pacific. It was only about 3 feet high by the time it actually made landfall in Hawaii and California and such.
Wasn't the tallest one in like Japan was like 100?
You mean historically? Yeah. Yes. So historically, when I say historically, there are paintings in Japan from feudal Japan, so I'm talking about like 1200, 1300 Japan, where there are artist representations of a wave that appears to be about 100 feet tall. Yeah?
The tallest reported tsunami in modern history.
Josh, who is this?
Hi.
This is the office.
Okay. Emma, you've been summoned.
And it was actually 1,720 feet. In Alaska.
Oh, you're talking about the wave.
1958.
Yeah, so the 1958 earthquake in Alaska, it was an earthquake that collapsed a hillside into the lake and caused basically all the water in the lake to turn into a wave. I don't know if there was a movie about it.
Okay, thank you, Josh.
I'm glad we got to tsunamis before you left. Bye. Okay. Yeah, so that was a special circumstance, okay? That wasn't an ocean tsunami. That was a tsunami caused by the collapse of a hillside, right? But
It's the tallest historic tsunami wave in the world.
So technically that is true. That is very true. Washed away an entire town right there on the side of the lake, if I believe. But yeah, ocean tsunamis don't typically get that big, right? The one in Japan that could have been up to 100 feet tall is the biggest one that I'm personally familiar with. However, if any of these asteroids that are circling our orbit right now ever actually do hit and land in the ocean, they would make very tall tsunamis because of the amount of water they displace. Okay? Earthquakes, though, that's one of the biggest reasons why we are focused on forecasting these things efficiently, because we want to keep something like this from ever happening again, right? Or at least to this extent. We can't stop them from happening, but ideally we would be able to know when they happen and, you know, that's what I'm looking for. Telling people to leave. Evacuate! My mind immediately went to exfiltrate. I was like, that's not right. Evacuate. Okay? Evacuate as many people as possible to keep people from getting killed.
So like they did like LOR drills, do they do like very prone areas, do they do like earthquake drills?
Yeah, and tsunami siren tests and all of that. They would have tsunami siren tests when I lived in Hawaii fairly often. Okay? So we have lots of sensors built up around places like Japan and Alaska and California and lots more in Indonesia and places like that to watch for these things. There are buoys that specifically telegraph the presence of tsunamis so that we can get the warning out fast enough.
They're like, hey, we're on the ground now.
No, not quite like that. But they do take note of changes in typical patterns of waves. So if they are calibrated to know, okay, so if I bob up and down, you know, and I bob up 4 or 5 feet or down 4 or 5 feet, it's because that's what the typical wave level is there. But there's a threshold. If it's like, I just went up 8 feet, then it sends a warning. If it's like, I just went up 20 feet, guys, then you know that something really bad is going on, right? And that's
What
what...
if it just like rocks because the tsunami pulls the water out?
So the tsunamis only pull the water out from the shoreline, right? You don't get that effect out in the middle of the ocean.
So you'll only see it like if you're looking at a beach.
Yes, if you're near a beach, yeah. And there's a whole movie about the 2004 earthquake called Unbelievable. No, it's the
I got
It's got Ewan McGregor in it.
The Impossible.
The Impossible, thank you. I knew it was some word, right? The Impossible, about this 2004 earthquake, and that's part of it. They see the water get yanked away from the shore and the tsunami moving in. Heartbreaking movie, by the way. Absolutely heartbreaking. Okay, so it's very important for us to watch out for these things, become familiar with how they might happen, and try and forecast them so that we can keep people alive, okay? It's very important that we do this right as geologists. There are geologists whose entire jobs are watching for these, gathering the data, and giving out warnings. Most of the time, they give out the warnings, and it's a good thing that they did, but sometimes there's boy who cried wolf sort of situations. When that happens enough times, people forget, hey, these guys are trying to save our lives. And so geologists get fired because they give out too many warnings. Because what happens, if I told the city of Odessa, I think there's going to be a 6.5 earthquake very, very, very soon. Evacuate. And they move as many people out as possible. Think about all the money that's lost from businesses. Think about the oil industry, right? Hundreds of millions of dollars potentially if everyone just left for a week and then nothing happened. Everyone's going to blame me, right?
Freaking Josh.
I know. That would be my name. Freaking Josh. That's what people would call me for the rest of my life, right? But, I mean, if it was my job, then that's my job. But sometimes people let that affect their judgment if they're afraid of losing their job, if they're not right. So back in 2009, there was a couple of geologists who had the opportunity to share that they believed there would be an earthquake, but they were afraid of losing their jobs. So they waited until they could collect more data, and they waited too long. There was an earthquake, people died. And as soon as it was found out that these guys could have given the warning but didn't, they went to prison. As far as I know, they are still there for essentially manslaughter because people died because they didn't do their jobs.
So what if like they say there's gonna be this like really bad earthquake, but the energy like diffuses faster than they thought it would?
The energy doesn't diffuse. It can't go anywhere unless it's released. That's the thing with an earthquake. There's only one way for that energy to be released.
If it diffuses, is there a way it will diffuse wider than imagine?
No, because the movement occurs in one location, and then the energy expands from there. Now, some trends to remember here. Where an earthquake happens, earthquakes are going to happen again. because the source of the stress that built up that stress in the first place doesn't just go away because the earthquake happened. As soon as the earthquake is done, it's going to start building up stress along the same fault plane all over again. So that is both good and bad. It's bad because there's going to be another earthquake eventually, but it's good because now we know where it can happen and about how much energy it's going to have associated with it when it goes off again. Okay? Now, we've also figured out how to use these waves in other aspects of science. I taught you before that the crust is made out of is solid and the mantle is solid, the outer core is liquid and the inner core is solid. How do we know that? Well, because we know how primary and secondary waves interact with other materials, we can send them down underground and see how they respond. Okay? They respond in 3 different ways. There is reflection, where a wave will simply encounter another material and bounce off of it. There is refraction, where my wave will pass through one material, encounter another, change its direction. And you can imagine this. An example of this is you have your glass of water and you put a straw in it, right? The image of the straw you're seeing above the water and the image below the water are offset. That's called refraction. Your eye is picking up the light from that straw in the water at a refracted angle. That's exactly what I'm talking about here. And then there is diffraction. Diffraction is when your wave will encounter another material and then kind of bounce along the edge of it before continuing on the other side. So by observing the behavior of waves in those 3 ways, we have been able to figure out, generally speaking, what the inside of our planet looks like. That's how we know the outer core is liquid, for example. Okay? Now, this brings us to plate tectonics. Plate tectonics is our current theory of what the surface of our planet is composed of and how it moves around, how all of these events occur. Okay? Prior to plate tectonics, people thought that all our continents were basically bumper boats floating around on an ocean of liquid rock, magma underground, and they would just bounce off each other and kind of just randomly move in different directions across the surface of our planet. But we know different now. It sounds fun, right? But plate tectonics essentially states that our entire surface of our planet is solid, and the different parts of it are getting pushed around by convection forces in the solid mantle underneath of us. Okay? There's evidence for this. Look at how our continents fit together. They clearly fit together and split apart, and come back together and split apart. There are layers of rock in Africa and South America that are exactly matchable, layer for layer, fossil for fossil. That can only happen if they were together at the same time while those layers were being deposited. Okay? There are fossils present in all of these different continents here from when we were all gathered together in different supercontinents, sometimes Pangea, sometimes before. Okay? We talk more about this concept in 1404, by the way, what all our supercontinents were and when they split apart and all of that. So this is the force that's driving that convection, or that plate tectonic movement. We have convection that makes these cells of rising heat and falling cold in the lower mantle, which feed convection cells in the upper mantle, which causes drag on the bottom of our plates here at the surface, making divergent, convergent, or transform motions. Now, because we know the direction of the continents as they are moving by convection right now, we can make these things called models, predictive models, of where the continents might be in the future. So here we have a model that shows where Earth's continents would be in about 50 million years if they continued on their current trajectories. Okay? Panama's gone. Atlantic and Pacific, they can all talk to each other again. Okay? Pass water between the 2 Americas there. Africa has finished moving north, completely crushed the Mediterranean Sea between itself and Europe. Now the Himalayan mountain range is continuous across the entirety of this continent. So we probably wouldn't call it the Himalayas anymore. We'd probably call it the Afro-Himalayan or something like that, because it's a combination of this mountain range and that mountain range now. Okay? Australia has moved so far north that the equator cuts right through the center of it. It's on its way further north. Where's Antarctica?
Still on the bottom.
Still hanging out. It's chilling.
Ha ha ha.
Thank you. 250 million years in the future, presumably, this is what we'll be looking at. Some combination of all these continents all squished together. The Atlantic doesn't exist anymore. It's this tiny little inland ocean now between North America, South America, and Africa. Someone went through the trouble of giving this a name. Neo-Pangea. I hope they didn't get paid for that. Right, the band's back together. Where's Antarctica?
Still on the bottom.
Still chilling. Why?
It's an introvert.
It's an introvert. It just doesn't want to hang out.
Right.
Not really.
Like it's full of dark room.
Why in all of these models does Antarctica just not move?
Because it's on the bottom of the earth.
Why would that matter if it's on the bottom of the Earth?
Because if it wouldn't move, it would melt, right?
Antarctica isn't made out of ice. It's just got ice on it. Antarctica is its own continent under all the ice. It can still move whether there's ice on it or not. Why isn't it? Continents move because of what?
Convection.
Convection. Antarctica is not moving currently and has not moved for the last 50-something million years, if I remember correct. It doesn't have any ongoing convection cells under it. That's not to say that it won't. It has in the past. It just doesn't right now. And because it's not moving anywhere right now, it's impossible for us to predict where it might go. So in all of these models, Antarctica stays the same. We can't model where it would go because it's not going anywhere right now. Does that make sense?
Same with the Arctic.
The Arctic isn't a continent. The Arctic is northern Greenland, northern Canada, and northern Russia, and a whole bunch of ice up there. There's no actual continent up there in the Arctic other than bits and pieces of other continents. Which is a question Chloe had yesterday. Okay. Now the last thing I want to talk about is rock magnetism. You've learned in the past that the dark silicate minerals, aka the ones that are rich in iron, that form at the bottom of the ocean in divergent plate boundaries, namely the ones that make basalt, pyroxene, amphibole, etc., they're rich in iron. Iron is magnetic. That means that when those minerals form, they form oriented towards the pole of magnetic north, just like a compass. However, once we started extracting samples from the bottom of the ocean, we started to realize that there were places at the bottom of the ocean where those minerals were pointed towards geographic north, where magnetic north is right now, and geographic south. And it would alternate. There would be strips of rock that were going north and some south, and some north and some south, and some north and some south, like you see in this image right here. What does this mean? We had no idea for a while. Then we figured it out. Once we were able to start observing our magnetic field, we realized Earth's magnetic field is not constant. Magnetic south and magnetic north poles occasionally flip. That's right. Geographic north is not always magnetic north. North America is currently in the magnetic North Pole, or magnetic North Hemisphere. But when it flips, which it has historically done and someday will again, the North Pole will be at the bottom of our planet.
So it
Literally just flips.
so we'll be upside down one day.
No, only magnetically. Geographically, nothing changes. However, here's a question. What happens when that changes? Right now, we're in the middle of a transition. We're not sure how far it's going to get. Back when I was a kid, the North Pole was in the middle of Canada. It had moved so far south that it was not at the top of our planet. It was in the middle of Canada, and the South Pole had moved accordingly as well. It has since wandered around to Russia. It's sitting in Russia right now. We are in what's called polar wandering. And a lot of people believe that this period of polar wandering is eventually going to end up with a total flip. We're about due for it. The last time it flipped was, gosh, 5,000, 6,000 years ago? I might be thinking about a different thing, but it was a while back. And that flips consistently. Like throughout geologic history, it'll flip, 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 flip. Now that we know what we're looking for, we can see it. So it's going to flip at some point. Now, when it does, what's it going to do to our electronics? Every GPS system is based on magnetic north being geographic north. When all of a sudden magnetic south is in Antarctica, what do our GPSs do? Maybe. I don't know. They sure won't function.
Take us to the wrong place.
Yeah, all right. I want to go to Canada. It takes you to Antarctica, right?
Or Mexico.
Or Mexico. No, I think that they'll just cease to function. Like a core aspect of their ability to function won't be accessible.
Wait, what about compasses?
Compasses will also point different directions. Compass doesn't know or care what hemisphere it's in. It cares where the poles are. To an extent. There are some aspects of a compass that do care about what hemisphere it's in, but I'm not getting into that. Magnetic physics isn't something we're talking about. Let's see, what else? Animals are going to be confused for a while. Whales, birds, lots of species of insects. A lot of those things actually navigate and migrate based upon Earth's magnetic field. When Earth's magnetic field switches polarity, it's going to be chaotic for a while. Our nice bubble of magnetism that protects us from lots of the solar and cosmic radiation is no longer going to be stable. It's going to take a while for it to restabilize itself in the new orientation. We're going to be receiving more radiation. Things might get hotter for a while. It could be easier for you to get sunburned. Our satellites are going to get crispified, right? That's another problem. So there's lots of things that could happen from this, but we only know about it and this pattern of that happening because of the geologic record of magnetism in rocks that we can observe. Okay, that's all I got for you today. Quick reminder, I'm about to open your lab exam. It will remain open until Monday. I'm also going to post the video for Lab 5 instructions. If you are still confused about how to do that, please let me know. Please, 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 for my students that are here in the classroom and any who this apply to online, finish Labs 1 through 4 before you take the lab exam, and then worry about Lab 5, okay? Get it done in that order, all right?